Okay, welcome back to part 5 of Griscom and land cover change analysis for Indonesia and Mozambique. In the last video, we had managed to derive the raster layer polygon for Mozambique for the raster layer that we color coded using symbology and then clipped to the Mozambique polygon of interest, and we kind of arrived at a breakdown of the pixel intensities by 50 bins, and this is the raster layer polygon we got. Now we are going to go from here into creating the estimate of reforestation potential for Mozambique, and we'll do the same shortly after for Indonesia. That's the goal of this video. Okay, let's get going. So we have the histogram open, and I kind of created a cover page and pulled in a sample slide from one of the previous times I'd done this analysis. So what I can do is I can delete this. I'll come in here. I will screenshot this using my keyboard shortcut, which in the case of my MacBook is Control-Shift-Command-4. I will paste this in. We're effectively trying to paste this histogram here, and I will set this out here. Next, I will format this, and I will recolor to the darker blue that you see here. And now we are well set, and we just need to then start filling out. We need to start filling out these numbers for each of the histogram bins, and then we'll compute the table below. So we want to keep looking at this histogram. So the first number is 441, right? So that's 441. That didn't work out well. Just need to edit it to 441. Okay, there it is. Then from 400 to 410 million is 14. So that number there is 14. Great. The next number is 44. So 500 to 510 million, we want to annotate that as 44. Okay, we've done that. Put that in closer to the histogram bar. Come on. Okay, you can see 44. Next is 600, 610 million is 52. So let's go there, make that a 52, and pull that in here. That's great. So the next number of interest is 367. So I will make that into a 367. Great. And let's copy that in. Bring that up there. That number is 1021. Clearly you can see the distribution is kind of skewed to the right. Gosh. Yeah, so it's skewed to the right. So you find more pixels that seem to point to a greater reforestation potential. So it really looks like more parts of this polygon are actually barren and reasonably suitable for reforestation. The last number here is 1270. Okay, just definitely can be faster ways for us to do it if we just automated the entire workflow using Python. I'll do that in another video. But now I'm just trying to set this up. But so let's go 0 and we fill out the table below. So 0 to 10, number of pixels 441. We have if we have two more cells there, so I have to insert rows above. I'll create some space by moving all this up. So we have space for a slightly larger table. We go 400 to 410 minus 14. You also see that really not only is the data set coarse and that is 750 meter resolution, you also see the number of actually pixel intensities are not very continuous when you actually plot it out as 50 bins. It's almost like a digital map to a certain extent where you have intensities between 400 to 410, 500 to 510, and things like that. Anyway, so our goal now is to fill out all of these values. That is the next step. Right? And then we're going to add the total number of pixels. We can do that by bringing it in here. We'll just create some color so we can see what we're doing. So bottom is we sum up all the pixels. That's 3209. The cell here seems to say area per pixel or meter square by pixel. We haven't really evaluated that yet, right? And we know that the this is the multiplier for hectareage per pixel. We know that that has to be something around 750 times 750 or very close to 56.25. I'll show you how we get the actual number for that later, but all of these are stats we're going to derive by kind of computing some kind of weighted averages. So the first thing we actually can compute and from there back out absolutely everything are the total areas in meter square and the total areas in hectares. And that for that we just need to be able to, and that I kind of compute in Python using a library called Shapely. So I'm going to go ahead and start setting myself up to be able to make those computations. I'm going to go pull down some historical. Hello, I was actually setting myself up in order to be able to calculate the areas, and I have just done that. So basically, this is the Python file in order to be able to compute areas. And I really just want to open the polygon for Mozambique, which is RR. We know that the EPSG code in meters is 2736. So I'm going to put that in and I'm going to calculate the areas in square kilometers and kilo hectares as that. Maybe I won't keep it in kilo hectares because we want it in hectares. Wait, we have that number. Look how big that is. It's a big polygon. And we're gonna also put in the area in hectares there. And now we can really start computing absolutely all the others. I'll just do some simple computations here to handle number formats. I just want to bring it in at max to two decimal places, and likewise here, maybe I'll even make that 0 for convenience. We don't really need two places of decimals, but here you can see, so we want meter squares per pixel, so we take a total area in meter squares divided by the total pixels. You see it kind of, since it's a 750 meter resolution, it's kind of got to be somewhere around there. Next thing we do is we kind of calculate the area, kind of proportion that based on the number of pixels we get because we're computing a reforestable area within that bucket. So we're going to do uh, 441 divided by 3209. I'll put a dollar there so that formula works properly as I drag it down times that. So I got the proportioned area there. Excellent. Yep, so those computations are fine. I'll again go and just get the number formats there the way I want them. Number 0 decimal places. Great, we have that. And I'll do the same here. And here, really, the area in hectares per pixel is kind of the same thing. That by the total area in hectares divided by total pixels, you're getting a number like 54.57 as opposed to 56.25 exactly. And that's kind of okay because Shapely computes the total hectare edge based on the polygon and the EPSG code and kind of accounts for the curvature of the earth when it translates the lat long coordinates, which are typically in degrees to meters. So there is expected to be some variation when you actually compute it in practice because maybe the whole pixel is not represented within the shape and we need to accept that. So now we once again compute the reforestable area there, and that is simply the number of pixels, which in this bucket is 441, divided by the total number of pixels, which is 3209 times the total area in hectares, and I'm going to drag that number down. Great, so we have just check another one, and that's perfectly computed. So again, once again, I'm going to like just do the number formatting and make it 0 decimal points. So you don't really need to worry. So I'm going to assume that everything between 0 and 10 hectares is 0. So actually, the total reforestable area then is actually the sum of all of these things. Uh, the last, starting from 400 to 410 through 900 to 910. That proportional area summed up is what is our reforestation potential out of the total hectareage of 175 kilohectares. So now that we've got all of that set, we can bravely then go ahead, copy this, and put it into our fields here that we want to fill out there. And just like that, we have nearly evaluated the potential. And what I will actually then do, just to make this extremely evident, I kind of put out a shape that is typically some kind of bracket like that to show that I'm only summing up that is my reforestation potential, and that's 151062 hectares. That is the reforestation potential as has been highlighted by Griscom et al. And I'll just make this explicit. Reforestation potential. Excellent. So we've computed that using Griscom, and next, ideally, we should corroborate this using some kind of land use, land cover change analysis using modest and dynamic world uh, satellite data sets, which we'll do after. Now that we know to go ahead and do this Griscom et al. Analysis, I'm going to go and replicate this for Indonesia very shortly. I'm going to close my prior ones here. I'll call this Mozambique, and I'll kind of open up my Indonesia analysis page here so that I have that analysis going. Here we are. So for Indonesia, I need to be able to create a slide deck and a Google Sheet. So I will call this Indonesia Griscom just for some computations. I will call this Griscom and land use land cover Indonesia for the, and I will first start by putting in a cover slide for this. I don't want to link it to the existing slide, and I want to call it the same thing analysis for an HP project 16,000 hectares in Indonesia. I will refine this based on specifically which region we discovered this to be at, but very quickly I just want to go over once again the simple generation of the raster layer histogram and the computation in the context of this. So I'll work a little faster this time, try to follow along. So we were in QGIS, and last time we kind of computed this raster, which was the clipped, that was the Griscom raster clipped to the RR polygon. And we compared this raster, which is Griscom Indonesia raster, clipped to the Indonesia polygon. Unlike in the case of Mozambique, since the Indonesia polygon is extraordinarily intricate and very downscaled and a smaller resolution, Griscom is not really fitting in. You'll have all but a few pixels. The promising thing is that these pixels are green, indicating potential. So we still want to go ahead and do this analysis. We won't rely on it too much. We don't think it's accurate. So I'll go ahead and start that by saying raster layer histogram here in order to create one, and I'll choose Griscom Indonesia. There's only one band, so we don't need to worry about that. And we know that we want this to be 50 pins. We don't want to save it as temporary file. We want to save it to file. I won't save it in Mozambique folder. I'll go up to downloads, and I know I'm working in the Indonesia MHP folder for Indonesia, and I'll just save it as hist for histogram. That done, I will run this process. The histogram has been generated. I can close it, and I can go to MHP and open up the Indonesia histogram. This looks slightly different from the Mozambique histogram. As you can see, it's extraordinarily sparse in the center, barely any pixels. Some pixels showing really low to no reforestation, and some pixels showing reforestation potential on the other extreme. So now we're going to just go ahead and do the math behind this and interpret it as is. We're not going to take this too seriously, like I said. So I'll copy this. I'll create another slide which we want to replicate for this, and I'll call this Indonesia 16 kilohectare polygon. There's actually a name that we are running with for this polygon. I will just add in that name as well. It's called HCVF. So that's the, I think it's some kind of, the name of the conservation area is called HCVF. It is the ground 50 pins. Let's delete this. Let's go back. This is the raster layer histogram here. I will use my screenshot tool, create a screenshot, bring it in, put it in there, stretch it out across there, and I will order send it to back. I will recolor that in Google Slides to the color that we tend to run with for these. We know from looking at this histogram that we have 0 to 10, we have 800 and 900. So I'll go ahead and delete all of these cells which are not needed. So this gives me a lot more space to make this polygon look slightly bigger and feel nicer. I think I like that. We don't need so many of these data labels here. If you see that the chart that it's generating in QGIS is actually based on plotly objects in Python, so but it's not generating a data label. That's why I have to annotate it. The first bar is 237. Right? The last two bars are 12 and 46. So 12 and 146, and we have 12. With that, I can go ahead and delete all of the other ones. I don't need this. I need this. I need this. Green, right there. 237. Oh, looks like we haven't updated the total count of pixels for Mozambique, so I'll go ahead and do that. That should read 2209. Great. And here that was 237 12 and 46. Great. So you just need to replicate exactly the same thing here. Bring that in. Get the color going in. And we have the total here, just 295. 295. Now we have to compute all the other cells, which starts with computing the total area in hectares and meters squared. Great. So here what I'm going to, instead of really changing the path too much by jumping 2 steps ahead and all that and introducing new to my folder structure, I will just close this notebook here, and what I will do is I will just go to my finder here and copy that notebook, which I know we need in order to compute the areas, and I will also create a copy of that in this folder where we have the shape files and we want to compute it. And I will, 1 second. Okay, sorry I had to stop there, but we were in the midst of computing the total area for the Indonesia polygon, right? So this was our histogram, this was what we were working on, and we basically had to compute that, and I had kind of copied in a copy of that notebook that we used to compute the area using Shapely into my Indonesia shapefile folder, and I just wanted to compute it for this shape, for which I wanted to take the name of the file, and I also need to know what the EPSG code needs to be. So I will search for epsg.io, and I will search for Indonesia in meters. I can only search for Indonesia. And here we are. And ideally, all of these tend to be large enough to cover the entire country. So as long as it's a unit that it's in meters, it'll work. So I'm going to choose this, which is 23830. So I change that to the EPSG code, and boom, we can calculate the area. Interesting. It appears that that polygon has been divided into multiple subregions, and so it it consists of it's actually doing this, applying this lambda function for the entire set of entire set of all the subpolygons, but I just want one number in the end. So we know that this data frame is called current shape, and we just know that what we really want is just the sum of all those areas of all those polygons, and I think that should work for square meters. And similarly, we do this for hectares. Hectares, it's kilo hectares, and times 1,000. So we have those numbers. Let's go there and plug that in. Formats are sticky, so it will stay in the format that we need it to. Let's go in here and see the area in meter square that we need to compute there is nothing but the total area of total polygon divided by total number of pixels. Similarly here, the area per pixel in hectares per pixel is total area in hectares divided by the total number of pixels, which does not seem to there by there. Nope. Sorry. Yep. And then once we paste it in there, we get it in the format that we need. Okay, that's great. So there you go, 55.24 kilohectares. That's fine. So now this area in meter square scaled is something like that times area, and we can drag that down. And similarly, this is equal to that by that dollar sign there times the total area in hectares, and I can drag it down. Great, so we have all the values that we need to then bring back into this table here. Excellent, we've just computed that, and we see that this, since we ignore the first bucket entirely because they're mostly zeros, we compute the total reforestation potential as only the sum of the last two, and it looks like we only have 3 kilohectares of reforestation space within the 16 kilohectares. And that, like I said, is not a great estimate. We know that it's not a great estimate because of how sparse and how coarse the resolution of this Griscom dataset is. But at least we have our Griscom estimates now, here for Indonesia and here for Mozambique. In the next video, we're going to do land cover change analysis using the MODIS yearly satellite dataset, which has 22 land cover classes, and we're going to do it using dynamic world and dynamic world dataset, which has 9 land cover classes. Okay, see you in the next video. Okay, welcome back to video number 6 in this series, Griscom and land use land cover change analysis using MODIS yearly and dynamic world land cover datasets. So last video we've actually finished solving for the Griscom potential analysis for Indonesia and Mozambique. Indonesia, we found there was like 3.2 kilohectares. Here we found it was 151 kilohectares in Mozambique. The reliability is more in Mozambique than it is in Indonesia, and we know about that. In this video, we're going to do the land cover change detection analysis. And just before we step into that, I just want to show what it is that we actually want to try to create. We want to try to create something that looks like this. Let me put it on slideshow. You see, basically, we are going to look at the land cover map, and we're going to look at it year on year, and we're going to see within the different land cover categories how they change, and consequently we add up all the forest percentage types and we see how the percentage forest changes over a period of about 10 years. We also take a snapshot for the current land cover, and that data set ends in end of 2020, so we'll take it for 2020. We want to see what the lay of the land looks like. We'll put an estimate of total area. We'll put a map with a polygon there to show what is it the area we're estimating. We'll calculate some average deforestation rates per annum over a 10-year period like 2011 to 2020. So we'll calculate a 10-year deforestation rate, calculate a 5-year deforestation rate as the difference between 2020 minus 2016 in percentage terms and the likes. And finally, we'll try to estimate red plus potential, ANR potential, total carbon market tonnage using certain calculations. In order to compute the tonnage, we will need to multiply the total area that we derive as reforestable times an average biomass density estimate, like in tons per hectare. In order to compute that, we will actually try to get above ground biomass, below ground biomass, and soil organic carbon at 1 meter depth and 2 meter depth, and try to build some kind of composite estimate of the total biomass density in that region that the soil can hold in order to be able to estimate what kind of tonnage we can get. We'll also probably go and look at some other data sets which may be a little bit dated, like 2000, which is called Global Forest Watch. So we'll go into our regions of interest, find the closest area to it, and we'll try to find some proxy for biomass tons per hectare. And then we'll derive a normalized estimate that we can actually use for our analysis. So our the example you see here is from Zimbabwe, but we're gonna go and do all of this for our polygons in Indonesia and Mozambique. So stay with me while I talk you through this. Let's start with Mozambique. All right, so let's get into QGIS. This was for Griscom. We don't need this anymore. Let's open a new file. Do you want to proceed? We'll use the scratch layers, no problem. Okay, so we're now on a new piece of paper altogether. Let's start with Mozambique. From my other screen, I am dragging in the Mozambique shapefile. This is our region of interest. And we also downloaded administrative boundaries. So I'm going to go ahead and pull in a level 1 administrative boundaries. It asks me the coordinates that it's specified is this in this whole TET coordinate system, which is EPSG 4326 or 2736, and I need to convert it to WGS 84. So I'm going to just say okay, it'll do the job. I'll pull the layer under this. There, looks already looking like some kind of map that we need to create, that we saw in that chart. So let's go and set it to a gray. Yeah, looks nice. And let's go and set this to a slightly darker green or something like that, like you see in the map. Great. So we know where our region of interest is. Amazing. So let's already get going with that. Take a screenshot, go in here, we'll go back to our Mozambique slides, and immediately after this we'll add a slide. We'll put it in there. We're working with that as our region of interest. We want to do some kind of annotations. I'll copy things like that. I'll also copy that because we want it to be called Mozambique. So we'll just go here, annotate that as Mozambique. But building one piece of the puzzle at a time, and this area is what we know to be called Reserva Recreativa. Right? So we've gotten that on there. Don't worry about the top bar and the bottom bar. Next we need is some kind of total area estimate. You need to always put it in the the left of it, you can put it on the right as well. It doesn't really matter so much, but we kind of want to build each of these estimates one piece at a time. For some of the others, we're going to rely on the satellite data. Right, so here we are. We need to populate an area in kilohectares. So let's go look at it. Okay, great. We already know that the total area in kilohectares is this. So that's great. Let's bring that in. Gosh. 175130. Don't need the third layer of precision. 17529.53 kilohectares. We can also just test that, I believe, by looking at properties and fields, I believe, or source. Oh, okay. Not to worry. Area here. Master area. Oh, not to worry. So let's go compute our area use like we do using Shapely. So this is what we had for Indonesia. We don't want that. Let's go in here. Let's double check that for Mozambique.